The biopharmaceutical industry experiences immense pressure to develop high-quality products in increasingly aggressive timelines. Secondary structure characterization is often too laborious or too unreliable with the current tools to be useful across all formulation conditions. This is where we come in, introducing the AQS3pro, powered by Microfluidic Modulation Spectroscopy, or MMS. The AQS3pro represents the next generation of protein structure determination platforms, providing a novel tool to strengthen the bioanalytical toolkit and provide critical insights during drug development. The AQS3pro aids in protein secondary structure characterization never before possible by combining IR spectroscopy with a more powerful light source, microfluidic flow cell, and fully automated sample handling to provide robust measurements with minimal hands-on time. In this demonstration, I'll be showing you how to load and run a 96 well plate with a pre-written protocol, along with how to analyze and interpret the data. Additionally, I will go through some of the key pieces of technology that we've used to increase the quality and reliability of IR measurements. The system is compatible with a 24 or 96 well plate. Today, I will be demoing how to run a stressed series of lysozyme samples in a 96 well plate. Because we are going to be modulating between sample and reference buffer to get a differential spectrum, all liquids should be loaded in pairs. Once the plate is loaded, we then place the well plate into the carrier and secure a rubber gasket to the top, since we need to create a good seal for the system to use instrument-grade inert gas to push the samples up into the flow cell. Lastly, the metal plate cover is secured to the top and our carrier is ready to be placed in the analyzing unit. It is oriented with the aligning pins in the back and secured with the two latches in the front. Coming over to the software, starting from the home screen, navigate to the Run Protocol window, and once you've selected the correct protocol, click Activate. Here, select your data set to be saved and configure an email address for notifications. Then select Start Protocol. Running this protocol is basically click and go. Now you can see the gantry will begin to move with the sample injector needles into position to start your testing. While the system is running, I will go over some of the key pieces of technology we've used to achieve high-quality automated data. The system has two units, the analyzing unit, also called the AU, and the electronics unit, also called the EU. The EU houses the CPU, liquid coolant, vacuum pump, and peristaltic pumps. The AU houses the sample loading area for the 24 or 96 well plate carrier, the sample injector needles, and the optics bench. The optics bench is really the heart of the system because that's where the quantum cascade laser, the microfluidic flow cell, and the detector are located. Sample and reference buffer are pushed up into the flow cell through the sample injector needles using an inert lab-grade gas. Once the liquid is in the flow cell, our quantum cascade laser surveys the amide 1 band of the IR spectrum. This is from about 1590 to 1710 wave numbers. This region is specific for protein secondary structure because it probes the backbone conformation of the protein. Our quantum cascade laser is about 100 times brighter than traditional FTIR light sources, which allows us greater sensitivity and allows us to measure from about 0.1 to over 200 mg per mil. Now taking a closer look at the flow cell, we modulate between sample and reference buffer in the laser sampling spot. This allows us to get a differential absorbance spectrum. Because of this, our sensitivity is much greater and our reproducibility is about 98%. Once the protocol has completed, we navigate to the Data Analysis window and select the data folder that you want to analyze. Open the settings and browse for the appropriate preset file. Hit Close and Save, and then Analyze. This is the window you will see when the analysis is complete. There are 9 tabs along the top that are automatically generated, and we will be going through them one at a time. The first window is the raw data, also known as the differential absorbance spectra. This will show up even before the analysis is complete. Below the spectra is the table where the samples are listed along with their nominal concentrations. In the next window, the raw differential absorbance spectra are converted into the absolute absorbance spectra by normalizing for concentration and interpolating at 1 wave number resolution. You can also see in the table that since the system is quantitative, we now have a fit concentration that the computer calculates based on the reference protein designated in the settings. From the absolute absorbance spectra, the software automatically calculates the second derivative plot. This allows you to see the individual features that make up the protein spectrum more sensitively. This is particularly useful at observing small or subtle changes due to the increase in resolution and the extreme repeatability among replicates. The second derivative plot is then inversed and baselined to get a similarity plot. This is called the similarity plot because we calculate the percent of area overlap compared to a control sample that you designate by checking the AO compare checkboxes, and this quantitates the percent similarity. We usually observe a similarity of above 98% and higher among replicates, which gives us a high degree of confidence in the data quality and repeatability. Going back for a second to the second derivative plot, the software also provides a comparison by subtracting the second derivative plots of the samples compared to the control sample that you specify in the delta compare checkbox. This shows where the change is occurring in your samples compared to your control sample. Here you can see the most significant change is occurring at about 1656 wave numbers. Our stability plot tracks specific wave numbers from each sample to monitor trends in the data. In this example, we are tracking the wave numbers 1642, 1656, and 1680, which represents beta sheet, alpha helix, and beta turn, respectively. In order to calculate the secondary structure distribution, we use Gaussian curve fitting of the similarity plot. Here, you can see the curves that were fit to the spectrum. Since each curve corresponds to a secondary structure feature, such as alpha helix or beta sheet, we can then calculate the percent higher order structure and show it in this bar graph. Here, you can see as lysozyme is incubated at 60 degrees Celsius, it loses alpha helical content and it gains beta turn and beta sheet structure. This graph also demonstrates the high sensitivity of the AQS3pro. Overall, the key benefits of the AQS3pro are that it can accelerate development by catching instability earlier in the drug development process, and the fully automated workflow saves time and money because we can load and run samples in a 24 or 96 well plate. The improvements in data quality with the AQS3pro allow for analysis of proteins over the widest concentration range. This allows for analysis without buffer interference and yields repeatability around 98%, giving confidence in the data quality and ability to observe small changes. Finally, the AQS3pro de-risks drug development due to the increases in data quality, allowing confident, accurate, and timely decision-making. To learn more about what the AQS3pro can do for your research, visit us at RedShiftBio.com and request a custom demo. See change with the AQS3pro.